Okay, so we're going to look at our next to last theorem, and that is the divergence theorem. And then after this, we'll look at Stokes' theorem. But so I want to kind of introduce Stokes the divergence theorem with an example here. I've got let's suppose I've got a closed surface, and you've got this egg-like thing here. Hope you can recognize my drawing as being three-dimensional. And I've kind of divided the surface into a top and the bottom. So I've got surface 1 on the bottom and surface 2 up top. And what I have is I have an orientation here for the normal vectors. The normal vectors are going outward. Okay. So you can see, like, for example, for this S2, let's suppose that for this S2, I'll call this Z is equal to G2 of XY. Okay. And when it comes time to get my normal vector, what I'll do, since it's going outward and upward this way, I'll just say, well, G of X, Y, Z is equal to Z minus G2 XY. Okay. And then when we get our gradient for that, we're going to have negative G2, the partial of G2x, negative, the partial of G2y, negative, and then 1. Okay? The difference between G and G1 and G2 is G2 describes the curve above this little part here. So I've just kind of divided it that way where I have the middle part. So when we talk about the gradient, and let me call this G2 here. Okay? When I talk about the gradient there, what I'm going to get is I'm going to get negative G2, well, G2x, right? So I'll just do this, negative G2y, and then 1. So that would be the gradient of that one, right? Okay. Now, if you look at G1, if you look at this graph on the bottom, then we have this. We have Z is equal to G1 XY. And then if I talk about G2 here, if I put it if I write it in this form, then what we're going to have is we're going to have G1 XY minus Z. And this is going to give us a normal vector pointing outward, and it's down here. Okay, so we've not done a lot of this kind of analysis, but you can see that if we talked about the gradient of G2, then what we're going to get is G1x, G1y, and negative 1 here. Okay. Oh, this is G1. Okay, I guess I was in the habit of calling it G2. Okay, now, so that's just some preliminaries, right? So does everybody see how that would be the normal if we're going outward? Now, another thing I want to remind you of is when we talk about the divergence of a vector field. So if we've got a vector field and we want the divergence of that vector field, okay? And I think we wrote it this way too. We said del dot F. We said that what that's going to be is going to be the partial of F with respect to X plus the partial of F with respect to Y plus the partial of F with respect, well, no, what am I doing? Let me go back here. This is the partial of the first term with respect to X, partial of the second term with respect to Y, and then the partial of the third term with respect to Z. Okay. Well, we have a vector field M, N, P, right? So that's how we define the divergence for a vector field that looks like this. It's got these components in here, and that's how we define the divergence. Okay, any questions? The divergence. Okay, now what I want to do is I want to go back and look at a vector field over this surface. I mean, a surface integral over this surface. And I'm going to do this. I'm going to say, well, this is my vector field. You know, I'll just do a generic one here. Okay, so there's my vector field. And I'm going to calculate, I'm going to go through and do some work with the surface integral. And remember, this is what our surface integral looks like for both of those surfaces, S1 and S2. So it's going to be over the entire surface, but I'm going to break it up. I'm going to do the surface integral for S1 and the surface integral for S2. That's what I'm going to do. And we're going to see if we can come up with some kind of shortcut or some kind of, well, we're going to see if we can arrive at the divergence theorem. But here's what we have. Now, I guess what I'll start with is G1. I'll start with this surface at the bottom. Okay? Now, so first of all, let me just go through here and see what this is going to look like. If we just work this out a little bit, notice what we have here. We have M, N, and P, and we're dotting that with N, and then we have ds. Okay, so I'll just expand that out a little bit. Now, what I'm going to do now is something that we can do with dot products, right? I can do this. I can write this way. I can say, well, I'm going to take this first component, which is the I component, right? And I'm going to dot that with N, right? I can do that, right? I'm distributing it through. Plus the nth component, or the nth term here, dotting that with N. And then finally the P, which is PK, and I will dot that with N. And then we've got all this times ds. Right? Is everybody okay with that? It's just, and if you're not convinced that what I did there was legal, you can put numbers in, right, and just run through it and you can see. Okay? And it's one of the properties of dot products that we've looked at before. Now, I'm going to break this apart because this is a double integral, and I can break this into components. So if I do that, I've got this double integral for mi dot n ds plus the double integral for nj dot n ds, and this next one, pk dot n ds. Okay? Everybody still okay with that? So I've still got vectors going on here, right? Even though, I mean, I've still got the dot product. I just haven't worked it out yet. Now, these three double integrals, they're pretty much the same. So what I want to do is I want to focus in on this last one. And what I can do with that one, I can do with each one of these. Okay, so I'm just going to look at this last integral here and really focus on it and see what we can do in working with this, this surface with this one right here, just this last part. Now notice what I have here is I have 0, 0, p dot n ds, right? So I kind of broke it down a little bit. Okay, does everybody see that? Okay, now, here's what I want to do. I want to rewrite this, and what I'm going to do is I'm going to rewrite it the way we normally do when we're getting ready to evaluate. In other words, we don't have the n and the ds. We have the gradient here for the n, and then we have dA. That's the way we always did it. So what I want to do is I want to look at this first surface, S1, and then I'll do the same thing for S2. Okay, so here we go. We're going to look at z is equal to, we have g1 xy, Okay? And because the integral, or because the vector is pointing down, the outward integral is pointing down, I'm going to write the gradient this way. And let me just drop subscripts for now and just say, okay, the gradient, well, okay, so we have g, x, y, z. Let me just write this. It's going to be g, x, y minus z. Okay? So now let's look at the gradient. The gradient then is going to be, and notice I've just dropped subscripts now. We understand we're dealing with that first curve. We got gx, gy, and -1. That's what we have. Now, with that in mind, I'm going to rewrite this integral. This little part here that we have. So what I have now is I have this. I have 0, 0, p, dot it with this thing. And actually, let me go ahead and make some changes here. Let me call this dA and over this region here. Okay, does everybody see that? Now, the next logical thing then would be just, okay, let's do the dot product then. So here we go. We've got this double integral. And now notice what we have. We have, we just have negative p. Oh, one thing. Okay, so look, here's what I have now. I have p, but I'm going to go ahead and put in here what it is. We've got x, y. Now remember, this is something I haven't put in yet, but instead of just writing p, I'm going to go ahead and, p is a function of x, y, and whatever z is. Well, in this case, z is g1 of x, y, and I do need to put that in. Okay, and then dA. Okay, does everybody see that? Any questions about that? Okay. Now, I think what I'll do is I'll leave that right there, okay? So what we've done is we've got the bottom surface. Now, I'm going to look at the top surface. And the top surface is going to be very similar. But the difference is going to be this. Notice that I have, well, I'm going to have this. I'm going to have 0, 0, p, x, y, g2 of xy. And I'm dotting that with this. Negative gx, negative gy, and 1. Okay? So see, there's a little bit of difference. This is what I had from the surface, the bottom surface. This is the top surface. Notice, because this z part is positive, right? So the vector's pointing outward, and it's pointing upward too, right? Okay, now I'm going to do the same thing to this as I did to the previous one. I'm just going to go ahead and do the dot product. And if I do the dot product, look what I get. I get r, and now I get p, x, y, g2 of xy dA. Okay, does everybody dig that? Any non-digging? Okay. Okay, so this is all straightforward, right? No one finds fault with this? So let me know if you do. Okay, now look. This is half of it, right? So look, here's what we've concluded. That if we want to look at the whole surface, so we have the surface integral over S. And we have f dot n ds. And we know that we can split that surface up, and we could write it this way. We could say, okay, well, this is S1 f dot n ds plus S2 f dot n ds, okay? So in other words, I just split that integral up. I did the bottom part, then I did the top part. Now, let's go back and put it together then. So let's look at this surface 1 that we did. The surface 1, where is it? The surface 1 is this one, right? This is our surface 1. Okay? And this down here, of course, is our surface 2. This is our surface 2. So what I want to do is I want to put those together. Okay, so here I go. Okay, so this one is going to be this. And then what do we have in there? We had P. Now this is surface 1, X, Y, and what was it? G1 XY dA. Now, and there was a negative out front, right? Now this one is like it, except it's P, X, Y, G2 XY dA. Look at that. Okay? Now, let me go ahead and put these together. And I've got these two integrals. Let me just put them together and see what we get then. And let me put the negative one second. That's going to be better because that's the way we're used to looking at it. So here's what I've got. I've got P, X, Y, G2, XY minus P, X, Y, G1, XY, and all of that dA, okay, right? Okay, does everybody dig that? Just put those bad boys together. And now, I don't like all of this mess, so here's what I'm going to do. I'm going to combine it in a very clever way. I'm going to say, okay, let's do it this way. Let's write this as P, X, Y, Z, and just have Z goes G2 of XY, G1 of XY, right? So this is kind of this is just a different way to write it, isn't it? Okay, because we know what this notation means, right? Okay, so now, okay, let me go to the next step then. So you might be saying, hey, look, let me do this. Let me do something even more clever. Let me write this. Let me put a third integral in there. And let me do this. Let me do partial of P with respect to Z dz. And let me have that going from G1 XY to G2 XY. Okay, so that also says the same thing, right? dA and R, right? That too says the same thing. Does everybody agree with that? Because P, you know, if I differentiate it with respect to Z, I get that. So that's the same thing. Well, heck, look at this. I might as well just say, well, look at here. Here's dz and dA. dA is like dy dx or dx dy. I put those together and I got dv, right? So why don't I just do this? Why don't I just do a triple integral over some over this solid region, right? And do this. Why don't I do that? That'll work, right? Now that is for the last term. And we could play this little game for every term if we wanted to. We could go back and do this for every term. But we might as well just do this. We might as well just say, okay, let's suppose that we have this little flux thing. And we can write it this way. We can say, okay, I'm going to write this as a triple integral over some, that's solid region. And I'll write it this way. Partial of m with respect to x plus partial n with respect to y plus partial p with respect to z dv. Ah, there. So look, we have this closed surface, and we have these orientation where our vectors are pointing outward, right? And we made this observation that we could write this thing as a triple integral. So maybe that would make things simpler for us, right? So this is not a proof of divergence theorem. This is like a special case of divergence theorem where you have a simple closed region, a simple closed surface, I should say. Okay. But that doesn't matter. I mean, you can kind of see where it comes from. So let's look at how this would be used. Look at this. Okay, so let's see how this would be used. So what I have here is I have a vector field and I have a surface. And what I want to do is I want to find this, and it's a closed surface because you've got these planes, right? You have the xz plane, the yz plane, and the xy plane, plus you have this plane up here, right, coming down. So we're looking at this. So here's kind of a picture of the closed surface that we're working with. But the bottom line is maybe we're not given a picture. We're just said, okay, evaluate this surface integral, and this is the vector field, and this is the surface. Well, here's what we want to do. We want to write our triple integral. Okay, and then divergence. We're going to use the divergence theorem. So the partial with respect to x, that's 1. The partial with respect to y, that's 2y. The partial with respect to z, there's 1. Whoops, dv. Now, at this point, all we have to do, we're no longer really looking at a surface integral, anything special. We're back when we were much younger, back in the previous chapter, right? We were so young back then and youthful, full of enthusiasm. Well, okay, so now we're just gonna work this. So let's see how we would do this. So, and of course, at this point, our objective is we have 2 plus 2y. Our objective is, well, okay, we got to figure out our bounds of integration. Now, probably what most everyone will do is solve for z and do z first. So I have z equals 6 minus 2x minus 2y. So I'll do that. I'll just do a dz. And it goes from 0 to 6 minus 2x minus 2y. There that is. Okay? Now, z is 0, so what we have here is we have 2x plus 2y equals 6. So now what we're trying to do is get the bounds on the xy plane. Well, that's like x plus y equals 3. So let me do y here. I'm going to go y goes from 0 to 3 minus x. Okay, I do y here. And then finally, I'm going to haul off and do x. X is going to go from 0 to 3. Now, what we have to do is evaluate that integral. And that integral is the same as evaluating that surface integral. Okay? How does that grab you? Okay, so there is us putting on our divergence theorem boots and tackling that surface integral. Any questions about that?